Hello, a great welcome to this series on earthquake-resistant design of structures explained through the code portions contained in ASCE SEI 722. Today we are at topic number 3, wherein we'll discuss in detail on risk-targeted ground motions, which essentially is an important parameter in seismic design criteria. So before getting into the details, I would request all of you to subscribe to the channel by clicking the button in the right corner of the screen. So let us see what exactly is the background behind risk-targeted ground motions. So that's why I put up a question, why risk-targeted ground motions? We obviously know that a probabilistic seismic hazard analysis, known as PSHA analysis, normally provide us a hazard curve to determine the maximum considered earthquake MCE that normally correspond to a 2% probability of accidents in 50 years. That is equivalent to a return period of 2475 years. So fine. So it provides us the design ground motions. So but the question is that, so if I design a structure using this uniform hazard design ground motion, does it really provide uniform levels of performance? So the answer is a big no. So while it ensures that the design motions correspond to a uniform hazard level, it do not provide the uniform levels of performance. And this is essentially because we know that the ground motion hazard shapes, it varies from one geographical region to the other, and also these design motions do not take into account the uncertainty in the structural capacity. So this means that we need to look into some basis that provide us the design ground motions considering both the hazard as well as the collapse probability of the structures. So for example, here I have provided a hazard curve that essentially covers, I think that 3 parameters, yes. So for example, if you see, let me just zoom this, yes. If you see the black one, that is for the peak ground acceleration, and the green one, that is corresponding to 0.2 second spectral acceleration, and the red one is for 1 second spectral acceleration. It does mean that I have presented hazard curves for 3 parameters, and you can see that along the x-axis we have the ground motion, which is expressed in terms of g, and along the y-axis is the annual frequency of accidents. So how do you select a design motion from this hazard curve? It is very simple. We know that the maximum considered earthquake is corresponding to 2% of accidents in 50 years, which is a return period of 2475 years, and that is equivalent to an annual frequency of approximately 0.0004. So if you draw a line, so 0.0004 is somewhere here. If you draw a horizontal line, it cuts, for example, the black curve somewhere here. And if you just extend this down vertical, I obtain the corresponding peak ground acceleration. For example, you can see that here it is approximately, say, 2.04 g, though I have not clearly marked it out. In a similar way, you can also obtain the spectral accelerations corresponding to the short periods of 0.2 as well as 1 second from these hazard curves. So considering that these hazard curves do not truly represent the so-called performance of the structures, we need to move to the risk-targeted ground motions. And this risk-targeted ground motions, popularly known as RTGM, is adopted in the 2009 National Earthquake Hazards Reduction Program (NEHRP) provisions, which adjust the uniform hazard design motions to achieve a targeted collapse probability of 1% in 50 years. So this is done by incorporating the full ground motion hazard curve and a notional fragility curve for structural collapse. So now it is very clear to you that this RTGM, that's a philosophy of a uniform risk that is used in the adoption of RTGM concept that takes care of both the ground motion hazard curve and also the structural collapse. And these ground motions are targeted based on a collapse risk of 1% in 50 years. So now it is very clear to us that the objective of the RTGM framework is to ensure a uniform structural performance in terms of collapse risk. And obviously, we know that this was not achieved in the case of a uniform hazard approach. This means that ASCE 722 now has shifted from the much older, what we call as the uniform hazard approach to a uniform risk level. And the ASCE 722 uses risk-targeted maximum considered earthquake, known as MCER, spectral response acceleration values for the specification of design earthquake motion. So remember, the risk level that forms the pivot for the calculation of the RTGM is a targeted collapse probability of 1% in 50 years. Now, if we have the location of a particular place in the United States, you can use the USGS website. The address is already provided here. And this website or the tool will provide you the RTGM value calculator for a given hazard data. So remember that, as discussed in the previous paragraph, the computation of the RTGM value requires two sets of data. One is the hazard data, and the second one is the collapse probability data, which is obtained or represented through the so-called notional fragility curve. So now we are very confident that yes, risk targeted considered both the ground hazard as well as the collapse probability of the structure. Now let us go a little bit ahead to understand what exactly is the procedure involved in the calculation of the RTGM values. So I would like to mention here that this procedure mentioned here below, that is not sourced from any textbook. It is directly taken from the USGS website link. So if you are interested, you can obviously go through the standard textbooks already available on this subject. Now let me just take you quickly through some basic procedures involved in the calculation of the RTGM values. The first one is a step one, unsampling the ground motion hazard curve. So we know that the PSHA provides you a ground motion hazard curve. We cannot straight away use this raw data. We need to do some kind of an adjustment. This is what we normally call as upsampling ground motion hazard data. For example, as you can see on the right side, I have presented a hazard curve that is prepared for the Los Angeles site. And you can see that the hazard data is plotted in terms of small circles. But the problem here is that as we are focusing on the risk calculations, we need to do a lot of numerical integration, which requires that the hazard curve need to have a larger resolution. And normally we can do the so-called interpolation or the extrapolation using the well-known cubic splines in the log space to achieve this purpose. Further, we should also ensure that the so-called hazard data have much appropriate or an extended range so that we achieve the required probability levels. And as per the experience, the ground motion hazard data that is used for the RTGM values should adequately cover a data or a range that is bounded by SA minimum value of 0.1 times SAUH, and a maximum bound for this hazard data is 10 times SAUH. Remember that SAUH is the uniform hazard ground motion level. For example, for this hazard data, we find that corresponding to a 2% probability of accidents in 50 years, we have got a ground motion level of 2.04 G, which means that our hazard data that is used for the RTGM calculation should have a bound covering 0.2 G and 20 G. That is very clear from this. It is taken up to 20 G level. So this is the first step. That means tuning the ground motion hazard curve in order to help us to arrive at an appropriate RTGM value. Now coming to the step 2. In step 2, we get into the risk calculations associated with the building, and this is normally done through the fragility curve. A typical fragility curve is provided over here. So if you are not comfortable with the fragility curves, just skip it, that's all, because this requires that you have to have some basic understanding what a fragility curve, why it is used, etc. Anyway, remember that a notional fragility curve requires three parameters. First one is the target collapse probability. If you get into ASCE 7, you will find that the required target collapse probability is a 10%. Then second one is every fragility curve need to be conditioned on a ground motion level. Normally, this is taken as the uniform hazard value, and to start with, though we use a uniform hazard value, you need to perform a number of iterations till the fragility curve produces the target collapse risk. And the third one is the log normal standard deviation of the collapse capacity beta, that's normally taken as 0.6. So for example, here is shown a standard fragility curve. You can see that along the x-axis we have got the 1 second spectral acceleration SA 1.0 expressed in G's, and along the y-axis we have the probability of collapse. But as you can see that here corresponding to 10%, so this fragility curve is conditioned so that at a spectral acceleration that is corresponding to the value obtained from the hazard curve 2.04 G, it produces a 10% conditional collapse probability. So this is the step 2. So we start from the hazard curve, process it, then we get into the fragility curve. Using all the three parameters, we obtain or we construct a fragility curve. So having the hazard curve and the fragility curve, now we straight away get into the calculation of the total collapse probability, or in other words, we are talking about the risk element. So the total analyzed rate of collapse, lambda col, can be obtained via numerical solution of the well-known integral risk. This is known as the risk integral. That is known as lambda col is equal to summation of lambda SA greater than C F capacity C into delta C. Now let me just explain you what all these terms are. Maybe that all these terms are totally new to you. Now here C is the collapse capacity in terms of IM, because this is to be obtained obviously from the fragility curve, and I have already provided you what was the collapse capacity in the earlier slide. So this is expressed in terms of IM, and here F capacity C is the probability density function associated with the collapse capacity. And this is clear that it is nothing but it's a derivative of the conditional fragility curve. It does mean that in step 2, you defined the conditional fragility curve. Now you have to develop another curve which is truly representing the probability density function of the collapse capacity, and this is obtained as a derivative of the conditional fragility curve, and a sample derivative of the conditional fragility curve is provided over here. And as you can see that along the x-axis it is again you got a spectral acceleration parameter, and along the y-axis we have the probability density of conditional collapse capacity. So this is essentially a probability density function. Now what is lambda SA over C? This is the analyzed rate at which the ground motion intensity exceeds the collapse capacity. Or in other words, you will find that this is nothing but summation of the product of the hazard curve multiplied by the derivative of the fragility curve. And the result is what is presented over this curve. And here I have written as a hazard curve multiplied by derivative of the fragility curve. And along the x-axis, it is the normal, the intensity measure, that's the spectral acceleration. And along the y-axis, it is the annual collapse frequency density. It's the annual collapse. So from this annual collapse, we need to obtain the cumulative collapse risk. So this is what is shown in the next slide. So this provides you the plot of the cumulative integral of hazard curve into derivative of fragility curve. And this curve obviously will provide you what is the cumulative analyzed collapse risk that is computed at the associated ground motion level. And as you can see from this plot that the probability risk that is reached is 0.000175. So this is the risk calculated. Now the problem is that normally this collapse risk value need to be converted because our codes always talk about a percent probability of collapse in Y years. So we need to convert this collapse risk into a percentage probability using this simple expression: peak collapse is equal to 1 minus lambda call raised to Y. When you put Y equal to 50 years and lambda call is equal to 0.000175, you obtain the percentage probability of collapse as 0.87 percentage. Remember, this 50-year collapse risk of a 0.87 percentage is less than target risk of 1% in 50 years. What does it mean? It does mean that we need to make some more calculations. This means that we started with a acceleration that corresponds to a return period of 2% in 50 years, and we selected the design ground motion as a starting value, but unfortunately we arrived only at a collapse risk of 0.87%. So remember that the computation of the risk targeted ground motion at a particular spectral acceleration or a particular time period value is nothing but is a trial and error process, and only when we obtain or we achieve a target risk of 1% in 50 years we'll be able to obtain the corresponding, the so-called ground motion. So now let me just tell you, so that's all about the procedure that is contained in the USGS website regarding the development of the risk targeted ground motion values. Now let me just tell you the risk targeted maximum considered earthquake MCER spectral acceleration values reported in the code. So ASCE 722 in clause 11.4.3 provides you 4 spectral acceleration parameters, that is obviously risk targeted maximum considered earthquake. So the first parameter is SS, that is 5% damned MCER value, and this is, remember, it's a spectral response acceleration parameter, or simply it's a spectral acceleration value at a period of 0.2 second for site class BC site conditions. And remember here S indicates the short period, that's equal to 0.2 second. The next one is S1, the parameter S1, that is again a spectral acceleration parameter but at a period of 1 second. That is why the suffix here as 1. Now the second one is a similar parameter SMS. SMS is very similar to SS except that it's a parameter that is adjusted for the site class effects. And then finally we have the parameter SM1 which is similar to S1 but adjusted for the site class effects. So remember that all these parameters, spectral acceleration parameters, are defined at 2 period values, one at a short period 0.2 second and the other one is pivoted around a period of 1 second. Now the ASCE hazard tool, the link I have provided over here, will help you to arrive at these 4 parameters once you provide the location of a place in United States. So now let us get into a little bit more detail into the ASCE hazard tool. Here I have provided a snapshot of the ASCE hazard tool. It will ask you some basic parameters. For example, it has asked me the address of the place where I want to obtain these parameters. I have typed it as Concord, California. And the code also I have provided, that's ASCE 722. And obviously we need to provide the risk category. I have provided as 2. And the site class is typed as a D-stiff soil. And it allows you to provide the output in terms either in the customer units or in SI. I have selected SI and I want the seismic. So once you provide all these parameters, it automatically provides you these 4 parameters. Look here, this is the report summary, and this under seismic data, it has provided me all these SS, that's 2.37 values, S1 0.77. Remember that these are the risk targeted spectral acceleration values at the short period and as well as at a period of 1 second. And then it also provided me the values SMS and SM1, which already takes into the site class into consideration. And those values are 2.15 and 1.66. Now, having obtained the risk targeted MCER spectral acceleration values, now we need to get into the design spectral acceleration parameters. Now, equation 11 for 1 and 11 for 2 of ASCE 722 provides you how to obtain the design earthquake response spectral values from the risk targeted values. For example, from SMS, how to obtain SDS. So SDS, that is the spectral acceleration corresponding to the design earthquake, is taken as 2/3 of SMS, that is a spectral acceleration anchored at a short period, and then the design earthquake spectral acceleration parameter as D1, which is anchored at 1 second period, is equal to 2/3 of SM1. So the report summary that comes from the ASCE tool also provide you the SDS and SD1. As you can see that here SDS, it is nothing but 2/3 of my SMS value, that is 1.2, 2/3 of 2.15, that is equal to 1.43, and SD1 is nothing but 2/3 of SM1, that is equal to 2/3 of 1.66, that is 1.11. So what does it mean? This means that the basic spectral acceleration parameters, namely SMS, SM1, SDS, and SD1, can be quickly obtained from the ASCE hazard tool once you know exactly the location of a place in the United States. So I think that that's all about this discussion. So if you have any queries or you want a discussion on some more topics, please put it through the comment box. So that's all. Thanks a lot for listening again. So have a nice day.